Hello and welcome again to FlippedHarber for Physics. In this video we're going to talk about the practice problems on page 100, numbers 19 through 20. Number 19. On Earth, a scale shows that you weigh 585 newtons. They want to know what is your mass and what would the scale read on the moon, where g is only equal to 1.60 meters per second squared. Now, looking at a free body diagram, for a person standing on a scale, there's only two important forces: the downward pull from gravity and the upward force, the normal force. Now that normal force is being provided by the scale, and that's actually what the scale is reading, is how big of a normal force does it have to apply to this person or to you. A simple sum of forces, I should set it equal to 0 because you're not accelerating up or down. Solving for m, we find out that we need to take the normal force, that is what the scale reads, and divide it by g. So we find out that your mass is 59.7 kilograms. Now in part B, what would the scale read on the moon? We need to go ahead, solve for the normal force, plug in that mass that we found, along with the g for the moon, 1.60 meters per second squared. And we find out that the normal force provided by the scale, that is what it's going to read, is only 95.5 newtons, about a sixth. It's usually what we use in physics. We say that the gravity on the moon is about 1/6 what it is here on the Earth. Now, number 20 says use the results from example problem 2 to answer questions about a scale in an elevator on Earth. What force would be exerted by the scale on a person in the following situations? Now, looking up example problem 2, what we need to take off of that problem is that the reading on the scale is equal to mass times acceleration plus mg. That is mass times acceleration plus weight. And for all of these, we're going to go ahead and use the mass from example problem 2. 75 kilograms is going to be our mass in all of these problems. So for part A, the elevator moves up at a constant speed. That means that our acceleration is 0. So we plug in our 75 kilogram mass, plug in 0 for acceleration and 9.80 for gravity. We find out that the scale reads 735 newtons. Now this is what would be referred to as the person's true weight. Anything else, because the elevator is accelerating differently, is referred to as apparent weight. Part B, the elevator slows at 2 meters per second squared while moving upward. Now that means that the acceleration is pointed down. So it's going to be a negative acceleration. So the scale actually reads only 585 newtons. You feel lighter at the end of an elevator trip when you're going up and the elevator starts to slow down. You feel lighter. You've probably experienced that. And a bathroom scale under your feet would actually show that as well. It would actually read less than your true weight. In part C, it speeds up at 2 meters per second squared while moving downward. Well, that acceleration is still pointed down, so we still plug in a -2 for acceleration. So the bathroom scale again reads 585 newtons. Again, you've probably experienced this in an elevator. If you're on the top floor and you start down, you feel light for an instant, and the bathroom scale would reflect that. In part D, if it's moving down at a constant speed, again acceleration is 0, so the bathroom scale again reads the 735 newtons for true weight. Part E is slows to a stop at a constant magnitude of acceleration. Okay, they're not telling me what the acceleration is, so I'm just going to leave an A in there for acceleration. So it's 735 newtons, the true weight, plus 75 kilograms times that acceleration. Alright, so that's it. Again, time for you to try some on your own. I'll see you in class and I'll see you online.